নাকি একবার? নীলাদ্রি, নীলাদ্রি, দিনটা চেঞ্জ হয়ে গেল রে। लाइट में रहेगा शुद्ध.
Constructs a simple interferometer. He flows water through it first in this direction, then he reverses the direction of water flow and sends water through it in the opposite direction. He sees that the fringe pattern moves as he changes the direction of the water flow. And from that, he can back out the velocity of light in a moving material. Today, we can understand this in terms of the relativistic addition of velocities. Here, C over N is the velocity of light in a stationary medium. V is the velocity with which the medium is moving, and this is the relativistic correction factor. We take this to first order. This is the equation for the velocity of light in a moving medium. Even today, people in this field call this the Fresnel drag coefficient. Now, I've mentioned that I'm very interested in slow light. Now, in slow light, the group index is very different from the refractive index. And Lorentz, early part of the 20th century, worked on this problem. And he showed that the velocity of light in a moving medium has this more complicated dependence on the refractive index and on the group index. So we set out to do this experiment. We used rubidium vapor as our slow light material. Just remind you here that at moderate temperature, it shows some very fine absorption lines. The scale here is in gigahertz, so these are very, very narrow features. We raise the temperature up to 150 Celsius, and we get complete attenuation, except for these two small windows here. And the rapid variation of transmission with frequency here leads to a very large value of the group index. And here we've measured the group index as a function of frequency. And you see that we can obtain group indices as large as about 200. So we set out to do this experiment. We used a continuous wave laser. We have a Sonic interferometer. So the one beam of light goes around the path like so. The other beam goes around the path like so. They interfere they interfere at the entrance plane of a camera. So what we find is that as we move the velocity, as we move the rubidium cell with velocities up to 1 meter per second, that the fringe pattern moves depending on the direction of the motion of the rubidium cell. And here, this summarizes our results. Here's the change in phase velocity plotted as a function of the temperature of the cell. Theory and experiment agree very well. Now, what is the point of this? Well, you can see here that the change in the phase velocity is much larger than the velocity of the rubidium cell itself. So we're looking to see whether we can build new sensitive interferometers based on this light drag effect. Now, what I just told you about is longitudinal photon drag. There's also a process known as transverse photon drag, first observed experimentally by Jones in 1972. And here's the idea. You have a block of glass or some other dielectric material. It's moving downward with a velocity v. A beam of light enters the material, and the beam gets displaced in propagating through this moving glass plate by an amount that I'm calling delta x. So, and it's almost as if the light is being dragged along with the motion of the glass block. And that's the origin of the name photon drag. Here's the formula that Jones was trying to verify, and indeed he did verify that the change in position depends on both the group index and the refractive index or phase index. Very small effect, only a 6 nanometer shift. He needed, this is before EIT or anything else, he needed to do a very, very precise measurement with good signal to noise ratio in order to see a displacement of only 6 nanometers in the position of the laser, in the position of the light beam. Okay, so Miles Paget, a good friend of mine in Glasgow, started thinking, well, isn't there something like rotary photon drag? We call this an image viewed through a spinning window. And this is something I would not have believed until I did the experiment. Here we have a glass rod. It is rotating. And when you look through the glass rod, here this is just a letter of the alphabet, letter A. The image is rotated by a small amount. So we wanted to see this effect, and let's see, you see this effect scales with the group index, and people who in the slow light community know how to get group indices of well, as much as 1 million really. So we did the experiment. Very simple setup, and we just have a bar of a beam of light in the shape of an I-beam, and when the slow light material, which happened to be ruby, is going clockwise, we see that this bar of light is rotated slightly clockwise. And when we rotate this ruby in the opposite direction, we see that the image is rotated in the other direction. So this is what I'm working on right now, and this is a joint project between my group and the group of Nir Davidson and Ofer Furstenberg at the Weizmann Institute in Israel. So I've been telling you about normal transverse drag. What we are interested in doing is finding a situation in which the group index is negative, and then we will find a negative value of the drag. The medium is moving to the right with velocity v naught, but the beam is actually shifted to the left in passing through this material. We once again used rubidium vapor, but now we used EIT, electromagnetically induced transparency. This leads to a very, very narrow absorption feature, and thus a very, very rapid variation of the refractive index with frequency. And then here are the results. Depending on how much we are detuned from the 2-photon resonance, we can either get a positive light drag, a negative light drag, or no light drag at all. If we're at a position where the refractive index is not changing with frequency. So that is work in progress. And this is the experimental setup, but I don't think let's not go through it in detail. I don't think we need to. Okay, so that was the first half of the talk, or maybe I should say the first segment of the talk, because the second part is longer. It's how to control the phase velocity and how to do so using epsilon near zero materials. So when I say epsilon, I mean the dielectric constant or the dielectric permittivity. So there's near zero index materials and epsilon near zero materials, basically different names for the same phenomenon. Then talk about the non-linear optical properties, and then metamaterials for ENZ, and finally applications for ENZ. So I call this a spoiler alert because I'm telling you where the talk is heading instead of just letting this build up to this conclusion. But here's the intuition for why the epsilon near zero condition is of interest in nonlinear optics. There are two standard ways of measuring a third order nonlinearity. You can talk about chi3, or you can talk about N2, and these two quantities are defined down here. But the relationship between N2 and chi3 is shown here. And you see that there's the refractive index and the real part of the refractive index appearing in this denominator. So if we are working under epsilon near zero conditions, the refractive index is going to be very close to zero. That means a very small denominator and a very large value of N2. So this is intuition. The real physics is more complicated than just this. But I think this, if nothing else, this was the motivation for us to do this study. I'm thinking that maybe we could get a very, very large value of N2 by this method. So, okay, why do I care? Well, because nonlinear optics is important for a variety of reasons, and I just list some of the applications that people are working on. However, the nonlinear response is usually much weaker than the linear response. It's so much weaker that it's very difficult to implement some of these ideas. So for decades, people have been trying to find ways to enhance the nonlinear response. They've looked at resonance interactions, plasmonic systems, electromagnetically induced transparency, and metamaterials. Now, in my work, we were using epsilon near zero materials, either homogeneous materials or metamaterials. We studied both of them. So very simply, what is the physics of near zero index materials? Well, we know that the wavelength of light is given by the vacuum wavelength divided by the refractive index. So if the refractive index is very, very small, the wavelength becomes very large, just symbolically shown it here. Also, the phase velocity of light is given by cease. The oscillations are in phase everywhere, even though the light, the field vector is oscillating at an optical frequency, maybe 10 to the 14th or 10 to the 15th hertz. Now, this the first reference I know to this behavior is 1953 incidence. You will get perfect reflection, total internal reflection. It's only when you come in at normal incidence that you can couple light into the medium itself. Now, from Snell's law, you see that any angle inside the material will obey Snell's law. So the question is, which direction does it really go? Well, to do this, we needed to do a wave optics simulation. Here is a wave entering this zero index material, and these are the phase fronts of the light. You see that the light really is traveling in all possible directions inside the material. Just one more example. I call these funny lenses. No matter how the light gets into the zero index material, it always leaves perpendicular to the surface. So this is how you can create a plane wave of light. This is how you can create a spherical wave of light. You can build very large area single transverse mode surface emitting lasers. Usually, if you make the size of the facet of a semiconductor laser, you'll find that it becomes overmoded, which you don't want. But if the gain medium has a real part of the refractive index that vanishes, everything will be emitted in a single mode, no matter how large this distance L is. And finally, perhaps obvious at this point, there is no Fabry-Perot interference. A beam of light passes through a zero index material and does not pick up any phase shift in doing so. Now, here, really all I'm doing is telling you what my definition is of the dielectric permittivity and the magnetic permeability. And well, it's straightforward to show from the equations of electromagnetism that the refractive index is the square root of epsilon times mu. And this tells us that the refractive index will vanish when either epsilon vanishes or mu vanishes or both of them vanish. Now, why is this important? Well, there's a problem with coupling light into a zero index material. And the problem is one of surface reflection. Well, there's always reflection from the boundary between two materials, and we can express the reflectivity in terms of this simple formula here, where Z is the impedance of the material, which is mu over epsilon. So we see that if epsilon is equal to 0 and mu is 1 or some other non-zero value, that the reflectivity will be 100%. So we really need materials in which both epsilon vanishes and mu vanishes, and they both vanish in such a way that the ratio of mu over epsilon remains finite. So this is the background motivation for people who are studying epsilon and mu near zero materials. Okay, so that was a rapid review of the physics of zero index materials. Let's now talk about nonlinear optical properties. And just to motivate this is a highly schematic. One of the prime applications of nonlinear optics is optical switching, well, for telecommunication. And this schematically shows a beam of light entering a switch, leaving a switch. Here's the control. And whether the control is on or off, it determines whether or not this input beam can transit the material. So what would you want for a good switch? Well, you'd want fast switching times, and you'd want it to be able to operate with weak fields. So and how do you quantify the strength of the nonlinear response? Well, that's by N2 or chi3, which I mentioned a little bit earlier in the talk. So we're back to this equation here, that we can get a very large value of N2 if we work under epsilon near zero conditions. The way to look at this is that chi3 is the fundamental material parameter. N2 is how chi3 shows up in particular situations. So chi3 remains the same, N2 increases as we approach an epsilon near zero behavior. Now, just at a conceptual level, how would you go about choosing an epsilon near zero material? Let's say I've convinced you that this is very interesting and you want to do some work on your own. So first of all, you can use an electrical conductor. All conductors display ENZ behavior at their reduced plasma frequency. Here's the Druda formula. which most metals obey at least to some approximation. And you can see by inspection that the real part of epsilon will vanish for a frequency that's given by the plasma frequency divided by the square root of epsilon infinity. So this works great, but you need, but it only works near the plasma frequency of a material. Now, what about electrical insulators? Well, there's another mechanism here. Dielectrics can show ENZ behavior at their phonon resonance, optical phonon resonance. And so there's a range in the mid-infrared where the phonon resonances occur for many materials. So, so this works fine at a limited range. There's metamaterials. Here you can design a material so that the ENZ or epsilon and mu near zero wavelengths occur at any desired value. For any of these methods, we want low loss. And for low loss, we want the imaginary part of epsilon to be as small as possible at the wavelength where the real part of epsilon vanishes. This is a challenge. We're usually working near a resonance, and near a resonance, the imaginary part of epsilon tends to be large. So you have to work really hard to try to find situations in which you have low loss, but still have the epsilon near zero behavior. Most of my work is based on indium tin oxide, or ITO. We recently reported that at its ENZ wavelength, ITO possesses a very, very large value of M2, 100 times larger than those of previously reported materials. So what is ITO? Well, it's a degenerate semiconductor, low loss, meaning that it's so highly doped as to be metal-like. It has a high density of free electrons, and the bulk plasma frequency corresponds to a wavelength of 1.24 microns. And let's see. So I've been working very hard on indium tin oxide. There's another refractive oxide, aluminum doped zinc oxide, which has also shown strong nonlinear effects. Okay, so here's our initial results on indium tin oxide. We got a commercial sample. We did ellipsometry on the material. And here is the real part of epsilon, the dielectric permittivity. And you see that the real part of epsilon vanishes at a wavelength of 1240 nanometers. We then did standard Z-scan measurements. We see that there is a pronounced resonance. There's a pronounced resonance in the N2, and the resonance is centered right at the epsilon near zero behavior. Epsilon near zero wavelength. I also show here, this red line is the N2 value for chalcogenide glass. This was previously thought to be the most nonlinear material available, and it doesn't even show up on the same scale. The overall change in refractive index of indium tin oxide is as large as 0.8. Here we've measured the real part of the refractive index, the imaginary part of the refractive index. The real part of the refractive index shows a very, very large shift, which can be very important for applications. And finally, we did a pump probe experiment that shows that the response time of indium tin oxide is in the picosecond range, meaning that it could support switching rates in the terahertz region. Let's skip this one. Okay. Why does epsilon near zero lead to large nonlinear response? Well, I've already told you that this is one way of understanding it. Actually, this is a specific case of something very simple. Let's say that the refractive index is a background value plus some change in refractive index. Epsilon is a background value plus some change in epsilon. So then how do we relate the two? Well, of course, the refractive index is the square root of epsilon, and we can factor out the background value of the refractive index, and then we make an approximation, and we find that the refractive index is the background value plus delta epsilon divided by twice the background index. So again, if the background index is very small, a change of epsilon will lead to a very large change in the refractive index. Something else. Here's the wave equation. Usually we think that the nonlinear polarization is a small perturbation to the propagation of light. But in an epsilon near zero material, this term disappears entirely. And the only thing governing the propagation of light is the nonlinear polarization. Just from Maxwell's equations themselves, you can manipulate them to show that this quantity on the left, this is the normalized growth rate of some nonlinear process, is proportional to the square root of mu over epsilon. So this is another way. I've been stressing that a small value of the real part of epsilon will lead to a large nonlinearity. This equation shows us that a large value of the magnetic permeability also leads to strong nonlinear results, strong nonlinear response. And detailed numerical integration confirms this behavior. So this is work done, collaboration between my group and Nader and Geta. And it's a very, very simple. We consider second harmonic generation. A2, the amplitude of the second harmonic is proportional to chi2 times the square of the incident field at the fundamental frequency that I'm calling A1. Delta K is the phase mismatch. For simplicity, we take delta K to vanish, and we just plot what we get. And here is the normalized second harmonic intensity, plotted as a function of propagation distance into the material. Sort of a typical case would be epsilon equal to 1, and we see that the growth rate is like so. But if epsilon is less than 1, say 0.1 or 0.01, we get a much more rapid growth rate. So the summary is that the one of the reasons why epsilon near 0 gives a large nonlinear response is just from the form of the couple amplitude equations. Now, I think, let me just skip a little bit, and let's talk about materials for epsilon near 0. And this slide here simply wants to show that there are a lot of people working on materials for epsilon near 0. There's studies involving homogeneous materials. There's studies involving metamaterials. So it's a big field. Now, this is a very recent result from my own group. We asked, do metamaterials also show enhanced nonlinear optical response at their E and Z wavelength? The work on indium tin oxide, that was a homogeneous material. What if we have a metamaterial? Do we get a large nonlinear response? And what do we mean by epsilon near 0? Is it the effective value of epsilon obtained by taking a proper average of the constituents? So we did this experiment. We will consider alternating layers of a metal and dielectric. We can change the relative amounts of metal in this structure. Here we're changing it from 10% to 90%. And you see that the dielectric permittivity vanishes along this line here. And we can make the epsilon near 0 wavelength be anywhere from 300 nanometers to 700 nanometers simply by changing the relative proportion of the metal and the dielectric. So we chose a silver thickness of 16 nanometers, silica thickness of 65 nanometers. We once again do our ellipsometry. We find that the real power of epsilon vanishes at 508 nanometers. We then did our Z-scan measurements. I won't go into the technical details of closed aperture and open aperture, but I think you can see just by looking. Here is pure silver. It gives a response down here. Here is the silver silica composite, nanocomposite metamaterial. It shows a much larger response. And this larger response is in rough agreement with theory. It's not as exact as one would want, but I think that the theory shows that you expect a large nonlinear response at the epsilon near zero wavelength, which is exactly what we saw in our experiment. Okay, applications of epsilon near zero materials. I especially wanted to save time for this because, look, if you're studying epsilon near zero materials and they're not useful for anything, why would you be studying it? So here's some of the applications of epsilon near zero materials. And I'll start off with what is really remarkable is that there's strongly relaxed phase matching requirements in epsilon near zero materials. This is what we were studying. It's a waveguide geometry, and epsilon near zero is obtained by having this honeycomb metamaterial structure. Okay, so, and we studied the process of four-wave mixing, in which two pump photons turn into a signal photon and an idler photon. Now, you expect the signal and the idler to be emitted in the forward direction, because that's what standard phase matching would tell you. But we find that the two pump photons going in the forward direction, we see processes in which the signal photon is in the forward direction and the idler is in the backwards direction. So this seems very strange, at least at first, but we remember that the phase matching condition depends on the Z component of the K vector, which is given by n omega over c. If the refractive index vanishes, then the wave vector vanishes. And that means that the phase matching condition can be automatically satisfied for a process like this, as well as for a process like this. So what is the significance? Well, nonlinear optical processes that were previously believed to be too weak to be useful can be excited through use of EMZ materials. So this is brand new, not published yet, but I think there's a lot of promise in seeing how these relaxed phase matching conditions can lead to new applications for nonlinear optics. Now, next is real-time holography with terahertz refresh rates. And to motivate this, let me remind you of this classic scene from the first Star Wars movie. And here's Princess Leia, or I should say a hologram of Princess Leia. The point I want to make is that with today's technology, we do not have holograms that can be refreshed at a video rate. The holographic materials are too slow. So our goal is to do real-time holography with video or much faster refresh rates. And of course, indium tin oxide is fast. It supports terahertz refresh rates. And this could have important applications involving image processing, signal processing, and of course, making movies, perhaps. So we did this experiment. We took a thin sample of indium tin oxide. We wrote a hologram into the material by interfering a signal beam with a reference beam. Then we later, which is to say within 1 picosecond, come in with a readout beam. This readout beam scatters off of this grating, to create a reconstructed signal beam and a conjugate beam. And here's the actual laboratory results. Our signal beam, well, we chose a petal beam. The reference beam is a Gaussian beam. These form the hologram. Then this is the readout beam, and this is the reconstructed signal, and this is the conjugate of the signal. So this has implications for work to follow. Next process is adiabatic wavelength conversion through time refraction. So let me explain what people mean by time refraction. Well, the usual refraction is space refraction. This gives us rise to Snell's law, for example. And the way this works is you have the refractive index that changes at some boundary. So as a function of Z, the refractive index versus N1 then changes to N2. When this happens, the frequency of the light remains the same, but the wavelength changes according to this relationship here. Now, there's something called time refraction. Let's think of a material in which at a sudden instant of time, the refractive index is changed everywhere in the material from N1 to N2. Now, in this situation, there's no mechanism for changing the wavelength, but it's the frequency that changes in accordance with this formula here. Now, in many ways, time refraction is simply an alternative way of understanding frequency broadening and shifting by self-phase modulation. Right. Classic explanation of self-phase modulation is that the change in frequency is the time rate of change of the nonlinear phase shift given by the usual result. But new insights from thinking about this in terms of time refraction. Just to give credit where it's deserved, there was previous work on adiabatic wavelength conversion from these references here. They were using a change in refractive index of maybe 10 to the minus 4, and they got a change in frequency of 0.06% of the carrier wave frequency. Now, our ENZ materials can obtain a much larger value of delta N, which suggests that we can get a much larger change in frequency. So here's our experimental setup. We used an optical parametric oscillator to obtain light at 1.24 microns. We split it into two beams, a probe beam, which just passes through our sample of indium tin oxide. The pump beam, here's the delay line, so we can control when the pump pulse arrives with respect to the probe pulse. And our sample, it was just two last slides containing indium tin oxide, flipped over face to face to effectively double the thickness of the indium tin oxide to 620 nanometers. And here are the results. Experiment and simulation, they're very, very good agreement. Let's take a look at the numbers. Here, as we control the time delay between the signal and the pump pulse, we change the frequency shift. The frequency shift can be made to be either positive or negative. The total shift, well, it's easier to say it in terms of wavelength. We get a total shift in wavelength of about 80 nanometers. And here the results are summarized in this graph here. So the observed effect is about 100 times larger with 100 times smaller propagation distance than previous reports of adiabatic wavelength conversion. So this is starting to sound useful. Application that we have in mind would be wavelength division multiplexing for telecommunication. And okay, the summary the summary is that very interesting physical processes occur in ENZ materials. ENZ materials display extremely large nonlinear response, and this large response lends itself to many important applications. And here I want to thank my students who are just remarkable and did all the work that I reported today. Here's my Rochester group. Here's my Ottawa group. I'm a full-time employee of the University of Ottawa. I've been given special permission to run a research group at Rochester as well. Oh, and research groups. So any of you who are undergraduates now looking for graduate school, any of you who are PhD students now interested in postdoctoral positions, please keep us in mind. And thank you very much again for the invitation to be here with you.
Thank you, Professor Boyd, for this enlightening talk. Now we are open for question and answer session. Yeah. Yes, so Professor Subhashis Dattagupta, you can go ahead and ask the question.
I'm not hearing anything.
Hello. Now I switched on. Can you hear me now?
Yes, I do.
Yeah, we are meeting over the net after a long time. Maybe 30 years or something. Okay, so I have a couple of questions, two questions. First one is about this imaginary part of chi3. So when you make this n0, refractive index close to 0, then you are enhancing the imaginary part also. You are enhancing the nonlinear absorption also.
I'm
So
sorry,
what is the imaginary part it plays? One. Second question is about chromoscopic relation. Well, can you comment about chromoscopic relation about such materials near this ENZ behavior?
There's a terrible echo.
Professor Dr. Gupta.
Yes.
So I'm going to mute myself and let's see if that helps. One. Somebody should say something so we see if the echo has gone away.
I guess it's
Hello?
okay now.
Should I repeat the question?
I think it is echoing. Professor Dr. Gupta, I think there are a lot of echoes that we could not hear.
You take over. You ask the question. I'll ask it. I'll send him a mail. No problem.
Maybe somebody.
I have a question if Professor Boyd. This is
Yes, I hear you.
Yeah.
Yes.
So this is just a simple question, that a query rather. So this when we talk about epsilon near zero materials, so of course the imaginary part of the epsilon, so that should poses some challenge, and particularly it is not possible to realize both real and the imaginary part of epsilon to be zero at a given frequency. How big a challenge is this? Because something similar also happens in the context of negative refractive index material. So practically, how big a challenge is this? So this is one question. And second thing is that it's not very clear to me that when you talk about metamaterials, so does the spatial structuring of epsilon or the spatial dispersion of epsilon helps in terms of realizing epsilon near zero material?
Okay, let's do them one at a time. I'm sorry, could you repeat the first question? I want to make sure I know what you're
Yeah, the
asking.
first question is that how big a challenge is that when we talk about the other effects like the enhancement of the nonlinear effect and the other effects. So epsilon, the imaginary part of epsilon, that cannot be zero, right? Simultaneously, that cannot be zero at a given frequency fundamentally. So how big a problem is that in terms of practical applications?
Sure. Okay. So a couple of answers here. I think Kramers-Kronig relations are fighting against you, but they don't say that epsilon. They don't say that the imaginary part of epsilon has to be large. It's an integral relation. So in concept, the imaginary part of epsilon can be very, very small, even in the epsilon near zero region. Second comment is that even though indium tin oxide is incredibly absorbing, the nonlinearity is so large that you only need to pass through maybe 100 nanometers of indium tin oxide to get a very large response. So, well, I guess I showed results. So the results would be even nicer if there was not absorption, but the absorption certainly did not kill us in displaying the effects that I showed. So I think that's all I really know about that point. And now your second question was what?
Yeah, so yeah, thank you for this. And the second question was on, I really did not understand that what role the spatial structuring or metamaterials plays in the context of realization of epsilon non-zero, epsilon near zero materials.
Okay, so I don't know. The one of the people who's been working on these metamaterials is Eric Mazur. It's very complicated. He is using Dirac cone metamaterials. And it's a lot of numerical analysis using something like numerical that allows him to control the refractive index. I do not know of any simple, intuitive explanation. So I think we leave it there.
Thank you. Yeah, I'm done.
So there is a question from Professor Subhashis Datta. He's asking, trick you can achieve epsilon near zero behavior. Can you use them for NLO, nonlinear optics enhancement?
I never thought of that. So thank you. Great suggestion. I don't know. If you want to continue this discussion by email, we can look into it together.
Professor Shauran Das has raised an hand. Sir, can you please unmute yourself?
Yeah, thank you. I have a question regarding this, this epsilon going to zero concept itself. In a sense, when you think of, if I'm not an expert in these materials, then what comes to my mind is you apply an electric field on an insulator, and then the dipole moments and the free charges, if there are any, they organize themselves in a certain way, and that is what the displacement field represents. Now, when the epsilon itself goes to zero, which is the linear response coefficient, and how should I think about the arrangement of charges if I look at it microscopically? Is there an understanding what you expect at a microscopic level? What is the organization of these charges which is giving rise to this effect?
Okay, good question. I mean, I understand. A good question. And I'm not sure I have a good answer. But I think one could say the same thing about how do I understand that the refractive index of glass is 1.5.
Yes. Yeah.
It's to ask exactly what is each electron doing is a much more difficult question
So has it been addressed? Can it be addressed at some level experimentally to see, zoom in and see this? What is setting in as you go to that limit?
I think the answer is yes. I think
Okay,
people are working on this. I say that at the atomic level, the atom doesn't know that it is in an epsilon near zero material. It is just giving rise to a response, a polarizability. And it's only when you take the collective sum of all the atoms in the material that you discover that you're in an epsilon near zero material. I don't see anything special that's going on at the atomic or molecular level. That is my answer at this moment, and I could be wrong.
Okay, so now the follow-up question, I think Nirmal also asked this question, that the imaginary part of this quantity will always crop up, which is kind of the bottleneck. But is there, you said that it can be small, but is there a estimate of how small it would be, in the sense that is there a quantum limit to that number? Is there a, in a sense, like 0-point oscillation, you know, is there a proper theoretical calculation which says that you can't reduce it beyond this because it's fundamentally that much? That's the limit, quantum limit to it. Is there a
great question?
Great
question. I'm not aware of anything along those lines. It could be that there just is no fundamental limit. It can be as small as one wants through careful material science. It could be that.
I see. But it's not known if there is a fundamental limit to that reduction. Let's say coming from uncertainty or something, that you just can't go beyond a certain point.
I'm giving a colloquium right now. I'll be at your meeting within 5 minutes.
Yeah.
Okay, sorry.
Thank you.
People are reminding me I'm supposed to be at a different meeting right now. So let's do one more question, and then I'll have to say goodbye.
Yeah. Okay, fine. Maybe I'm done. If time permits, I have one more question, but maybe I'll just shut up here and then let others ask questions.
Yeah. So in the chat box, there is one more question from Professor Datta Gupta. What about the Kramer's chronic relation of such nonlinear responses in epsilon near zero materials?
Just repeat that. I want to get the details.
What about the Kramer's chronic relation of such nonlinear responses in epsilon near zero materials?
Okay. Kramer's chronic relations were originally derived for linear response. To a limited sense, we can apply Kramer's chronic relations to nonlinear response. I've thought a little bit about this, and I haven't been able to find anything particularly interesting or illuminating from the study of Kramer's chronic relations. But that's not to say that there isn't something very interesting there. It's just that I haven't found anything so far.
Okay. So there are two more questions in the chat box. Is it okay that we read it out?
But why don't you read it? But my responses are going to have to be very, very short. But please go ahead.
Yeah. Anirban Ghosh, what will be the Brewster angle in case light impinges from air onto a epsilon near zero material?
I don't know, but it's I don't know. I think we can just work it out. I think the standard rules apply. But good question. Good question. I wish I had the answer. You've given me motivation to think about that question. Okay, and the last one?
From Chinmay Bishwas, in the closed aperture, Z-scan of metamaterial, silver silicon dioxide, why the valley and the peak is so asymmetric with respect to focus?
Oh, let's see. If a material has a non-linearity both in both the real and the imaginary parts of the refractive index, you tend to get these asymmetric traces. And I think the answer is no deeper than that.
I hope there are no more questions in the chat session. With this, maybe we can end the session. Once again, I thank Professor Boyd for accepting our invitation to give a kickstart to our Department of Physical Sciences colloquium for this academic annual year, and for the OPTICA chapter colloquium. Thank you, Professor Boyd, for an interesting talk. Use physically when you visit IISER Kolkata next time.
Right, I will try to visit. Who knows when that will be? And thank you for the invitation. I enjoy meeting people and talking about science. So I better sign off now.
Thank
Goodbye.
you very much. Thank you all.